the last chapter of the tutorial will go back to my very first experiments I've shown in the beginning. And this is the simulation of H2 pulses to cells incubated with excess sulfate or nitrate. So these are electron donor pulses or reductant pulse method, and the cells will behave quite different to what we had before because they are incubated under N2 and excess of electron acceptor, so they don't need to start with transport of the electron acceptor, and furthermore they will be oxidized. There is no excess of electron donors, but instead the H2 comes in and slightly increases the electron availability, and the reactions are slower and the curves are looking different. And although we have the same components, the same metabolites in our assays, the reactions are different, as we can see, and the proton translocation is different as well. And these experiments are done also in the presence of KSCN, so we should see proton translocation, and we do. And you see here 14, 34 and 68 nanomoles of H2 were added, and then you see some protons coming out and disappearing again, and you can see the simulation is quite good, especially here for the larger pulse here and the medium pulse. And let's look at the simulation. So I stop here this presentation and show the graphic again as overlay, and you see I don't go into details. It's a nice simulation, and we change one single number to get from this complex curve, this different steep increase, then there's a steady state phase with increasing proton levels, and then a decrease at a certain time. So you need to know quite a lot of parameters to simulate this events, and we just change one single number and say show graphic. Okay, and then we go here and you see we come out really quite nicely, and that means, and we go here to, how much was it, 14, we go to 14, show graphics, and you come to this curve, and that means we can be quite sure that our simulation is really assuming realistic data. So let's look what the data tell us. Back to 68 perhaps is the nicest simulation. So what is different from before? So in the last proton translocation experiments we had a value of 1.6, if I remember right. Here we are perfectly fine with a value of 1. The ATPase rate is low, it was 0.015, here it's 0.027. I don't know what that means, probably not much. However, this value of 1 proton per electron could erase if the cells have a periplasmic hydrogenase that oxidizes H2, our electron donor, outside of the cell and channels the electrons into the cell via cytochrome C. That's quite well known from disulfovibrio. And then inside the electrons are consumed, and this is called the vectorial electron transport. So the proton can stay outside, is not pumped out, it's just staying outside, and then it will be consumed inside of the cell. So that would be a good idea to explain this. And then we don't have here any uptake of the electron acceptor. So we had with sulfate, we had -2 here, and we don't see it. And actually, if you look at the total reaction, it's not an alkalinization according to our equations that we had before. Instead, we get some acidification. So it's even getting more protons, and it's a scalar acidification. And that means clearly that we don't have the same reactions as before. And obviously the cells have started to form some compounds during the pre-incubation phase without H2. There was oxidation potential, and there were some compounds, some metabolites, I don't know what it is, formed, and these are now reduced instead of sulfate. And I can tell you with nitrate, we got the same vectorial proton translocation of 1. So in this case, it doesn't play a role whether there is sulfate or nitrate present. The cells will behave quite similar. And what we see is H2 oxidation, possibly periplasmic, and reduction of some compound we don't know yet. But it's still a good insight in the metabolism and energy and bioenergetics of a cell. That's it.